start the recording. Okay, there we go. So the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Anything higher, we basically have to it's like brute force it. So anything higher in degree, we brute force it, so to speak. So we have to kind of guess and check on what might be a 0, and then you try it. If it works, then you factor it out. If it doesn't work, you try a different number. And basically, you keep doing that process until you get to a quadratic, and then you use the quadratic formula. So you have to basically keep dividing out something until you get down to something that's an x squared, because then we know what to do from there. So there is a formula for cubics. Let me look that up right now. Okay, I'm just going to take a screenshot of this because I'm not even going to type it. It's really gross. So if you have something that's x cubed, you can use this really gross formula, and this is why we don't teach it. You look at it, to find x, it's a cubed root of this really gross thing with square roots inside the cubed root, and then you have to add another cubed root with more square roots, and actually it keeps going. And then you've got this little term here. Really gross. So there is a formula. Let me paste in the website this came from, if you really want to know more about it, but we don't use this formula because it's just really gross. So we brute force essentially everything, and that's what a computer does actually as well. If you have a computer that is trying to find zeros, it does essentially what is called Newton's method, where it just guesses and checks until it finds it. And so that's sort of what we do by hand too. I mean, there's no other way to do it other than trying to find formulas like this, and they're really difficult. And let's see, it looks like on this website it says that there's no formula for anything of degree 5. It's been proved that there is no formula for that at all. Degree 4 is even worse than this formula, so the easiest thing is to brute force. So basically, you're just going to try to factor. Now, in order to try to factor these things, we just guess and check, and there are infinite numbers that we can guess. You can't just, if you just tried with no rhyme or reason any number to try to guess to factor out, it's unlikely that you're going to pick the right number, especially if it's a fraction. If the 0 is a fraction, you're more likely to pick whole numbers, and it's going to be near impossible to try to figure these out. So we have these other theorems to help us narrow down our choices, so that you're not just picking out of an infinite choice of numbers, but you have a specific list of numbers to try. And then that makes your life easier. And these theorems are used in the computer as well. I mean, this is what the computer uses to do the Newton's method, is it has these rules. And so the first one that we have is the rational zero theorem. And so the rational zero theorem says if you have some function, polynomial, and it is in this form, so the a's are the coefficients, and we have our degrees just going down. So it just goes from highest to lowest degree. This first coefficient, the leading coefficient, the highest one, can refer to as q, and then the constant that doesn't have your variable with it at all is p. And so you identify your p and your q, and first you write down all the factors of each of those. And Then you write down all the factors of P, and then all the factors of Q. And you can either have a plus version or a minus version, and that basically lists all of your choices. So these are all possible zeros. So it kind of narrows it down to the possible numbers to try. Now, just as a reminder, factors are numbers that divide into the other one, I guess. I don't know what phrase to read it. So a factor of like 4 is a number that divides into 4. So those are what factors are. So you're writing down all the numbers that you can divide into the number that you have. So all the numbers that divide into whatever P is, all the numbers that divide into what Q is. And then that gives your list of possible zeros. So okay, that's going to be gross. I'm going to take example 1, or you know what? I'll just take the skill practice out of the textbook because that will be fine. So let's say we have this polynomial f of x equals negative 4x to the 4th plus 5x cubed minus 7x squared plus 8. So this is a degree 4 polynomial because 4 is the highest exponent. And q is the leading coefficient, so that's going to be negative 4. P is your constant term, which is 8. Now, the fact that q is negative, that positive, that doesn't really matter because we're doing plus and minus. So the sign really doesn't matter. What matters is the number. So we're going to start by writing down all the factors of P. So all the numbers that divide into 8, because that's what P is. So we can divide 8 by 1, by 2, by 4, and by 8. So those are all the numbers that divide evenly into 8. And then we want to have the factors of Q. So Q, if we treat it as 4, we can divide 4 by 1, 2, and 4. So our possible factors, we basically are writing a fraction based off of all the combinations. You're writing every possible combination of fraction that you can get from these sets, where P, the factors of P are the numerator, and the factors of Q are the denominator. So an easy way to do this is to actually sort of make a table. So I'm going to put P across, and then Q going down, putting those factors down. And so we've got this table here, and we want to fill this in. And so up here, these are the factors of P. This is Q, and it's plus or minus P over Q as our possibility. So you're just using this table to write your fractions. So I'm going to go from the top left and then move to the right. So we have plus or minus 1 over 1, which is just 1. Then we have plus or minus 2 over 1, which is 2. Then we get plus or minus 4 over 1, and then plus or minus 8 over 1. So those all come out with whole numbers because our denominator Q is 1. Then we could go to the next row, and now here our denominator is 2. So we're going to have 1/2. Then I've got 2 over 2, which is equal to 1. So we just have 1 again. So if it repeats, you could just kind of cross that out because we don't need to write it more than once. Then we have plus or minus 4 over 2, which is equal to 2. So that's already written, so we can kind of cross that one out. And then 8 over 2 is equal to 4, and we also have that one written down, so we can kind of cross that one out. Then we're going to move to the next row. And now our denominator is 4. So we get plus or minus 1/4. Then we have plus or minus 2/4, which reduces to 1/2. So I've already got that one written down. Then plus or minus 4/4 is 1, which is already written down. And then plus or minus 8/4, that reduces to 2, which we also have written down. So you're writing every possible combination, and then if it's a repeat, you don't need to really write it anymore. And then all of those numbers that we haven't crossed out, those are the possible zeros. So our possible zeros, we have plus or minus 1. So that means that it could be positive 1 or it could be negative 1. We've got plus or minus 2. So we could have positive 2 or negative 2 as a 0. Plus or minus 4, plus or minus 8, plus or minus 1/2, and plus or minus 1/4. So we've got 1, 2, 3, 4, 5, 6 numbers, 2 signs, so that's 12 different choices here for zeros. So by using the rational zero theorem, instead of having an infinite number of numbers to try to figure out as a factor, we have 12 numbers. So we have narrowed the pool quite a bit. And so now you're basically guessing and checking, but you only have 12 numbers to guess and check versus an infinite number to check. So that's the rational zero theorem, and that's how that is handy. There's another theorem that we can use to even narrow this down for us, and that is Descartes' rule of signs. So, and Descartes' rule of signs usually confuses people, but it's not so bad. So what Descartes' rule of signs does is it tells us how many of each sign, like how many positive zeros you have and how many negative zeros you have, or how many are going to be complex numbers. So if you use these two rules in conjunction, you know which numbers to check, and then you know how many are going to be positive, how many are going to be negative. So if Descartes' rule of signs tells you there's going to be 0 positives, then you don't even want to try positive numbers. So Descartes' rule of signs allows us to narrow this down further. So this tells us how many zeros of each type. And so we're considering positive, negative, and then complex numbers. And the number of zeros you have always adds up to the degree. So this is a 4th degree polynomial, so there's going to be 4 zeros. Now, explaining Descartes' rule of signs is kind of complicated. So first, we have the number of positive zeros. So that is equal to the number of sign changes in the coefficients of the function or 2 less. Or you can have 4 less or 6 less. Basically, you just keep subtracting down by 2 until you, I mean, if you subtracted by 2 and you ended up with like -1, you can't have a -1 number of zeros, so that just doesn't count. As long as you can subtract 2 and stay in the positive numbers, you could have 4 positive zeros or 2 positive zeros, or maybe you have 3 positive zeros or 1 positive zero. But they're always kind of subtracting by 2. Then the number of negative zeros. So that is equal to the number of signs, or the number of sign changes specifically, in the coefficients of f of negative x. So you plug in negative x instead of positive x, and then you look at the signs. So, and that is also, you subtract them by 2. So you could also have 2 less than that, or 4 less. So they're always in pairs, essentially. So if you think of it, your choices come in pairs. And then the number of complex zeros this is equal to the degree minus the number of positive minus the number of negative, because they have to add up to the degree. So if it's not a positive real number, if it's not a negative real number, it's got to be complex. And complex zeros also always come in pairs. So it's not possible to have one complex zero because they always come in pairs. So you always have to have 0 or 2 or 4 of these things. And that's why we have the -2 for this pattern, is because these things tend to come in pairs. And with complex zeros, they're always complex conjugates. So these come in pairs. And they are complex conjugates. And that means that basically they're the same numbers, just opposite signs. So if you find one complex zero, you automatically know the second one. So that's a really nice skill. So between these two rules, this helps narrow down your guessing and checking and your brute force, so that way you can find your zeros smartly. So once you've used these things, once you've figured out what numbers you need to try, and then you figure out, okay, we need to do Descartes to real signs, then you basically use synthetic division in order to test these. So first, we need to actually do Descartes to real signs on our example that I have here. So I'm going to rewrite, it's the same example. So we have f of x equals -4 x to the 4th plus 5x cubed minus 7x squared plus 8. Okay, so we're going to first find the number of positive zeros. And so you just look at your coefficients. We have a -4, we have a 5, we have a -7, and then we would have a 0 for an x term because we don't have an x term, and then we have 8. So those coefficients are the same things you look at when you do synthetic division. And you look at how many times it changes sign. So it changes sign from -4 to 5 because those are opposite in sign. And then we change sign again from 5 to -7. And then basically you go from -7 to 0 or 8. Either way, those are basically kind of the same thing as considered. Zeros doesn't really have a sign. So we have 3 sign changes here. So it changes sign 3 times. And so that tells us we have 3 positive zeros. So we want to make sure we try positive numbers, or 1 positive zero. So if we have 3 or we have 1, we know that at least one of the numbers is positive, because those are our two choices, basically. So we know that one of the numbers has to be positive, and so we should be checking positive numbers when we try to find our zeros. So next is the negative zeros. And so for this, you have to first find f of negative x before you can do the coefficients. So you replace x with negative x everywhere because you're plugging that in. And then you're simplifying. So negative x is the same thing as negative 1 times x. And negative 1 to the 4th power to an even power is equal to 1. So that means negative x to an even power is the same thing as x. So this just gives us x squared back out. But negative 1 to an odd power gives you a negative answer, because negative times a negative times a negative is odd, or is negative at the end. So any negative x to an odd power is going to give you a negative answer, and so that flips the sign. So instead of a plus 5x cubed, it's going to be a negative 5x cubed. Now when you square a negative x, you become positive. A negative times a negative is a positive, so that stays as negative 7x squared, because negative x squared is x squared. And then we have our plus 8. So the only thing that changes signs are those things with the odd exponents. Everything else stays the same. And then we look at our exponents. And again, I can just, there would be a 0 there. I'm not even going to bother writing it because 0 is neither positive nor negative. It's special. Now, how many times did we change signs? Once. We have negative, then we stayed negative, then we stayed negative, and then we move positive. So we have one sign change. And this tells us that we have one negative 0. If we subtracted 1 by 2, we get negative 1. You can't have a negative number of things. So far what we know is that out of the zeros for this function, at least one of them is positive. We know for sure we have a negative 1, so we need to make sure we try negatives. And then the remaining 2, it may either still be positive or they could be complex numbers. So we sort of make a chart here. So positive, negative, and complex. So we could have 3 positive or 1 positive. We know that we have 1 negative, so for either possibility there's at least 1. And then these have to add up to 4. So if 3 of them are positive and 1 is negative, 0 of them are complex. But if we have 1 positive, 1 negative, then we need to have 2 complex in order for those to add up to 4, because that's the degree of our polynomial. So these are our choices. We know for sure we're going to have a negative 0. And so because we know we have a negative 0, I would start by trying negative numbers. So you go back to your list of possible zeros, and you're just going to do synthetic division on these. And we'll try all the negatives first until we find one that is a 0. And we use synthetic division because it's quicker. So we're going to use synthetic division to factor. So we have negative 4, 5, negative 7, 0, and 8. So those are the same coefficients that I wrote down for a number of positive zeros. And you need to include the 0 because we need to have a spot for every spot of the x, going down from the highest exponent down to the lowest. So I don't write my synthetic division exactly like the way that the book does. I sort of write it with a table. They write it making it look like division, but that's not what I do. I write it like this. I think this makes more sense to me because it's I don't have to rewrite things. I don't know. This just works for me. So we know we have a -0. So I want to start trying negative numbers out of my possible zeros here. So I'm going to actually highlight this so that I can. So I usually start with the whole numbers, and then when I've tried every whole number, then I do the fractions. So I'm going to just start with, and I know I have to have one negative, so I'm going to start with -1 and see if that's a 0. So I'm going to go down to my synthetic division, and I'm going to try -1. So now with the synthetic division, that first number always drops down. And then you're multiplying these numbers together. So -1 times -4 is 4. And then 4 plus 5 is 9. So this is how I write my synthetic division. And then you multiply. -1 times 9 is -9. -9 minus 7 is -16. -1 times -16 is 16. 16 plus 0 is 16. -1 times 16 is -16. -16 plus 8 is -8. So if we don't get 0, it's not a 0. And this is where the brute force or the guessing and checking comes in, as you're basically just trying every number until you get one that works. So what I do is, because I've put it in this form, I just reuse it and I just say, okay, now I'm going to try my next number. So I go back to that list of possible zeros, and now let's try -2. That's the next number on my list of possible zeros. So I just make a new row, and then I repeat the process. Because all you're doing is multiplying and adding, you can just do that on your calculator. You don't even really have to write the steps if you don't want to. You just have to make sure you're keeping track. So -2 times -4 is a positive 8, and 8 plus 5 is 13. So then you have -2 times 13, which is a -26, and then -26 plus -7 gives me -33. -33 times -2 is 66. Plus 0 is 66. You can see my numbers are getting way farther away from 0, so this for sure is not a 0. And then 66 times -2, and then we add 8. And now we're at -124. So this is also not a 0. Now the thing about synthetic division is these are giving us y values. So if I went from an x of -2 to, or -1 to -2, my y value got even more negative. I'm trying to get closer to 0. So this seems to be taking me farther away from 0. So this might be one area where I'm like, okay, then maybe I don't want to try these whole numbers. I might want to try like -1/2, because that seems like that will get me closer to 0, and that is on our list. So you have to kind of look at your numbers and look at what it means and say, okay, well, maybe I want to try something else. So I'm going to try -1/2 because I think that will get me closer to 0 as an output. And this is where having a calculator that does fractions is very handy, or you could just use the decimal version. That's fine enough, but we do like to keep it as fractions. So I'm going to actually pull out my calculator that does fractions nicely. So you have a -1/2 times 4, or times a -4, and so that's +2. Then I add 5, and so that gives me 7. Then I multiply 7 by -1/2 plus -7. I get -21/2. Multiply it by -1/2 plus 0 That gave me 21 over 4. Multiply that by negative 1/2 plus 8. Okay, that gave me 43 over 8, which, as I put as a decimal, is a positive 13. So this is also not a 0. So far, it might be kind of helpful to sort of look at a graph or kind of visualize what's going on here. So let's say this is -1, -1/2. That would be a -2. So these numbers that I'm finding that I'm testing to see if they're 0. They're also values on a graph. So -1 was about, like, let's say this is at -8. -1/2 came out at approximately a positive 13. So that's like somewhere up here roughly. And then -2 was way, way, way down in the negatives because that was like -124. So if you're kind of graphing this, you can see that we're going to cross somewhere between -1 and -1/2. Now the problem is none of my numbers that I have in my possible zeros are one of those numbers. The next one would be like -1/4. And that means it's not going to be a rational number. What this means is that whatever that number is probably something that has a square root in it. And so that's not something that I can guess and check. That's something that I'm going to only be able to find once we simplify this further. So this is telling me I can't narrow down in that area just yet. I need to find a different number. So this is where we start thinking about end behavior. So there's a lot of stuff we're learning about polynomials that kind of help you narrow this down, because this is really the only process that you can do here. So our polynomial is upside down because our end behavior says what is it going to happen based off of the leading coefficient and the degree. So we have something that's x to the 4th, and an even power looks like a u. And negative means it's an upside down u. So our shape is going to roughly look like an upside down u. So looking at my graph, this is probably going to keep going down lower, but up here, I need to eventually turn around because I need to somehow get this upside down u. So that means there must be some 0 here in the positives, especially because we know only one 0 is negative, because that's what Descartes' rule of signs told us. Only one of them is negative, and we've determined it's got to be something with the square root, so we can't find it with this method. So that means I need to start trying positive numbers because I need to know where that other side is. So you use all of your information here. This is where the real critical thinking, problem solving goes, so that you can try to take this all into account. So now I'm going to just start trying the positive version of these numbers. So I'm going to start with a positive one because 1 is easy to start with. So you've got 1 times -4 plus 5. So that gives me 1. 1 times 1 is 1 plus -7, -6. 1 times -6 is -6 plus 0 is still -6. 1 times -6, of course, is -6 plus 8, and we get 2. So if I were to graph this, so 1 is roughly here at 2. So now I know, okay, this thing's turning around here, and it's turning around quickly. So my 0, I'm trying to make this a little better, has got to be somewhere after 1, so let's try 2. It's got to be on the other side of that based off of where my numbers are coming here. Oops, make sure I keep all my numbers. Okay, so now I'm going to do 2 times -4 plus 5. And oops, it gives me -3. 2 times -3 is -6 plus -7, -13, Then we have 2 times negative 13 is negative 26 plus 0. And then 2 times negative 26, negative 52 plus 8. Okay, negative 44. Okay, so this means, looking at my graph, so if we're at like 2, this means 2 is at like negative 44, somewhere down here. So it's crossed somewhere between 1 and 2. So now I'm going to go back to my possible zeros list here. So far, none of the numbers on this list are between 1 and 2. It's the same problem that we had on the negative side. So none of the numbers are between 1 and 2, which means that they must be something with a square root. And this rational zero theorem doesn't apply to those. So that must mean that both of these numbers involve square roots, which would have to come from the quadratic formula. And then, because we don't have any way to get a rational zero, the other two must be complex numbers. So you look at this and you're like, okay, so here's what we figured out. We have 1 negative 0 that needs to involve a square root. And we also have 1 positive 0 that involves a square root, because we could not find it. Basically, our choices don't allow us to find those two numbers based off of our graph. And because none of these choices based off our picture are on a zero or rational zero list, so based on picture, none of the zero locations are in the possible zero list. It's likely they are complex zeros. So what do we do with a thing like this? When we're trying numbers, and so far none of the numbers seem to work. So to be safe, you could say, okay, I'm going to go through every number on the possible zero list because it's possible this turns around, but knowing the shape of it, it's very unlikely it's going to turn around. So the second thing you can do is say, well, let me graph this just to see if there's anything I'm missing. So you want to go to desmos.com and graph it. So let's see, what is our function here? Let me make sure I typed -4. Oh, I had a typo. Okay. So when you bring it up in Desmos, this is what it looks like. So it's got the upside down U, and then you can see these two zeros. And when I click on them, they're the nasty decimals, and that means that, yes, these are going to come from, eventually, if you're trying to do this, you would have the quadratic formula at some point. You would find the two complex zeros, and then you would have remaining two more, which you can get from the quadratic formula. So you can use the graph to verify everything that we figured out. And at this point, the only way to find out those exact values is by using something called Newton's method, which we don't teach in this class because it's a lot of hard work. Generally what happens, and so I just picked this particular problem just from one of the examples. Usually what the book does and what we do on the homework is we pick them very carefully so that there is always going to be some real zeros. So you're not going to come into this situation. But this is a more likely issue in real life. In real life, they're not nicely picked. In real life, you end up things where you're like, oh, I can't really find the exact number. I have to sort of approximate it. But the book will find things, and you'll use the synthetic division. You'll find things that are a zero, and then what you do is you divide that out. And then, so if we had an x to the fourth and we found one of these zeros, we would divide that expression out. And then we have an x cubed. And then you go through the same process. And you would do the rational zero theorem on the x cubed. And you would use Descartes' rule signs, narrow it down. And then you would divide that out. And then you end up with an x squared. And then once you have an x squared, you just use the quadratic formula. So it's a lengthy process, these zeros, but zeros are so important because in calculus, you're always finding zeros because you're always trying to maximize something or minimize something. When you maximize or minimize a function, you're taking what is called a derivative, which is basically looking at the slope of the graph over all time, and it gets you some equation that demonstrates the slope, and then you find the zeros, and those zeros are where the maximum and the minimum points are. So in real life, a lot of times we're trying to figure out how can I get the maximum cost? How can I or maybe I want maximum revenue, but I want to minimize my cost. And so in order to do those things, you have to first get an equation that represents your costs, and then you're finding zeros. And so this is why this is so important. We spend all this time on it, but it is a very lengthy process. And we use a computer to do it most of the time because you can see it's a lot of guessing and checking. But what's important is understanding what all of these rules do and how they help you, and understanding what's going on the back end, because your computer is basically doing all of this. It's going through all these rules because a computer can just brute force it really quickly. So they're trying all of the numbers on our rational zero list, and then when it runs out of those and none of them are good, then it goes to another method. But it's basically going through all these things. So I just happened to pick an example that I thought the example I picked was only for the rational zero theorem. So then I went and I took it behind and said, okay, let's actually find the zeros, which then ended up being a nasty problem. Not easy to find the zeros. But this is what the process is. And so when you're finding zeros, you're basically just factoring, and you're using synthetic division to find those factors. And you keep removing something until you get to something you can do the quadratic formula on. So does that help make anything you read make sense? A little bit. Yeah, I would recommend going through example by example, making sure that you can reproduce the work they're doing and that you understand what's going on, and watching the videos that are embedded in the ebook. I think that will help. And it's a matter of knowing the rules, and on like the homework and the quiz, they're basically like kind of leading you, like use the rational zero theorem or use Descartes' rule signs. Or if they'll say find the zeros, basically you know that you have to do those things first, and then it's just kind of guessing and checking. But this is like a big picture of finding zeros and combining all of these things together. But I mean, like it's there's a lot of little moving pieces that you have to understand first, and so that's where you want to make sure you get through all of each section, and you have to really understand the concepts because they all fit together. Example 4 in section 7.4 goes through this. It doesn't use Descartes' rule signs, but it goes through an example where they're basically guessing and checking until they find a 0. And then they actually do it by factoring using special factors instead of using synthetic division, because they tried all of the synthetic division steps and it didn't work, because it's going to be one that's got a square root, or they end up with one with a complex number. So sometimes you have to try some different tricks. But I would take a look at that example because it kind of shows you the tricks and some of the things that you can do. But 7.4 has lots of examples, and it's just a matter of practicing the rules and then knowing what rules to do.